Hello, grade 8. So this week we are going to continue with our chapter 2, Mechanical Action and Forces. Let's start. Now, these are the objectives that we're going to cover during this week's lecture. So you guys will be able to represent a force by a vector. So you'll be able to draw this force. And you will be able to distinguish between a contact force and a force at a distance. Now, we're not going to be able to cover the forces at a distance. That is for another lecture, but you will be able to tell the difference between these two, and we will list some of the contact forces. I'm going to review the characteristics of a force because we're going to need those for the representation of a force by a vector. Okay, so the first characteristic is the point of application, which is the point where the force is actually applied at this point. This is where the force is applied. This is what we call point of application. Okay. The second characteristic is the line of action. It's a line. It could be horizontal, vertical, or oblique. So it could be horizontal, it could be vertical, or it could be oblique. Okay, so it's a line of action. It could be vertical, horizontal, or oblique. Okay, so these are the only three options for the line of action. But for the direction, it means that we have maybe two forces having the same line of action, but one is pointing up and the other is pointing down. Do I say these two forces are the same? No, they have different directions. They share the same line of action, but they have different directions. The one's pointing up, it means that its direction is upward. The one's pointing down, its direction is downward. How about like this? They have the same line of action, which is horizontal, but one is directed to the right, the other one is directed to the left. Now, if I have, just like that, an oblique line of action, this one is upward to the left, and this one is downward to the right. And the other way, this one is upward to the right and then downward to the left. All right? And the last characteristic is the magnitude. Okay, it means like what is the value of this force, how much it is worth. How can I know that this force is bigger than that one? Okay, two forces, they might have the same point of application, same line of action, direction, but they are different. How is that? Because they have different magnitudes. Okay, so a magnitude is actually a characteristic of a force and can be measured using a spring balance. So these are different types, we said, of spring balances, and they give us the reading, they give us the value of this force. So it is measured by a spring balance. We also call it a dynamometer. Its SI unit is Newton. So this is the SI unit of the magnitude of the force. Okay, so now that I know that a force is characterized by its point of application, line of action, direction, and magnitude, I am able to represent this force by a vector. Okay, so I am able to actually draw this force. Let's see. We have a certain application, so I will explain this part using an application. It says represent using the scale. 1 centimeter gives 3 Newton. A vertical force F1 directed downwards with a magnitude of 15 newtons and applied at point C. So we have different points here, A, B, C, and there is a certain force here, F2. They're not asking us about this. Let's leave it now. Okay, so I need to represent a force F1. How can I draw this force? How can I draw the vector of this force? I can't draw it without writing down its characteristics. So let's start at first. So we say what characteristics of F1. Okay, what do we have? First of all, we have point of application. Can you tell me what is the point of application? Applied at point C. So the point of application is C. Okay. Now, how about the line of action? What is the line of action here? It could be vertical, horizontal, or oblique. So what does it say? It says a vertical force. So the line of action, you see, vertical force. The line of action is vertical. How about the direction? The direction, it could be to the right, to the left, upwards, downwards. It says here directed downwards, so it is downwards. Great. Now I'm left with the magnitude. Do I have the magnitude? Is it given? Yes, it's a magnitude of 15 Newton. Can I draw this force? Let's see. So the point of application is C. We can see C. We can see C. The line of action is vertical, so it is along this line. Great. The direction is downward. So I know that the force will start at point C and it will go down. Okay, so let me draw it. Start as C and it will go down. Okay, just like that. Just like that. Great, but how long should I draw this arrow? Like I could draw it this way or I could draw it maybe, I don't know, that way. Okay, so how can I know? This is where the magnitude comes in handy. Okay, so this is where the magnitude comes in handy. It says 15 Newton. Now check your rulers. What is the unit on your rulers? Is it Newton? Can you draw a line in newtons? Like, can you draw a 15 Newton line? No, we cannot. It's not, Newton is not the it's not a unit for length, okay? So your ruler represents a length, centimeters. So how can I actually draw this 15 Newton? I need to use the scale. It's really important, guys, okay? So we need to use the scale. What is the scale given? Can you tell me? It says every 1 centimeter represents 3 Newton, okay? So I have 15 Newtons. I need to know how many centimeters is that. So where do I put the 15 Newtons? Below the 3 Newtons or below the centimeters? Below the Newtons. So 15 Newtons, great. And now I have X. This is unknown. I need to find it. Cross multiplication, guys. So 1 centimeter times 15 Newtons divided by 3. So it becomes 1 centimeter times 15 Newton divided by 3 Newtons. We cross out the Newtons and then we are left with 15 divided by 3 is 5 and the unit is centimeters. Okay, so we are left with centimeters. Now I can draw it. Now I can bring a ruler and simply just to draw 5 centimeters. So this is 5 centimeters. Draw it downwards. So this is vertical downwards and its magnitude is 15 newtons, but it is represented by this scale. Part 2 says, give the characteristics of the force F2. So F2 is already drawn, like right here. Knowing that it is drawn using a scale, every 1 centimeter represents 3 newtons. So I need to write the characteristics of F2. So I write characteristics of F2. Okay, so we start with the point of application. So this is point of application. It's what? It's A. Then line. Guys, you need to write the whole point of application, okay? Not this abbreviation. Line of action. Line of action is what? What do you think? Is it vertical, horizontal, or oblique? It's oblique. Now the direction. The direction, what do you think? It is upwards, to the right or left? To the right. So it's upwards to the right. And now how about the magnitude? What do you think? Okay, it says here it is 3. This is in centimeters. Okay, so it's 3 centimeters. Okay, 3 centimeters. Is this the magnitude? Is the magnitude of force is in centimeters? Nope. I need to use the scale. So this scale helps me not convert, like represent from, just change between centimeters and newtons. Just, okay, keep that in mind. The scale helps me move from centimeters to newtons and from newtons to centimeters, because when I want to draw a force, okay, I need its length I need the length of the vector, and for me to find the length, I need the scale because I cannot represent it in newtons. But now I need the magnitude, so I need newtons. I don't have newtons, I have centimeters, so I use the scale. What does the scale say? The scale it says like every 1 centimeter gives me 3 newtons. Okay, so I have 3 centimeters now. Where do I put the 3? Below the centimeters or below the newtons? Centimeters below centimeters and newtons below newtons. Okay, so I need to find the x, and the x is the magnitude here. So x equals cross multiplication. Okay, so 3 centimeters times 3 newtons divided by 1 centimeter. We cross out, let me change color. So we cross out the centimeters. I'm left out with 9 what? Newtons. So the magnitude is 9 newtons. Okay, that's it. You just gave the characteristics. So these are the characteristics of F2. Now I know that not all forces are the same. Of course not, because they have different characteristics. So they have different point of applications, line of actions, directions, magnitudes. We get that. But despite all that, we can still divide the forces into 2 types. The first one we call contact forces. The second one we call forces acting from a distance. Now let's try to define each type. Contact forces, from the name of it, it's called contact forces. So it is the force that happens due to the contact between the 2 bodies, between the 2 objects. So there must be some sort of contact. Okay, they must touch in a way. So let's say you are trying to push a table, or you're trying to push a wall. Okay, there is a contact between your hand and the wall. There is a contact between your hand and the table. Let's say you're trying to lift a box. There is a contact between your hands and the box. So this is called contact force, okay, because it happened due to the contact between the 2 bodies. So it appears due to the contact between 2 bodies. Now, what is the second type of force? What is it? Like it's a magic thing? Like I can make something move without even touching it? How is this possible? Is it magic? No, it's not. It's physics, actually. So we have some forces that act from a distance or at a distance. It means 2 bodies can be not touching, okay, can have no sort of contact between them, but yet one body is acting, is applying a force on the second body. How is that? What is the first thing that comes to your mind? Maybe this picture, right? Magnet. Yeah, so if I have, let's say, a piece of metal and I have a magnet right here, the piece of metal will get attracted to this magnet and it will move. Okay, so how am I able to see the force? I can see the force by seeing this object move, okay, because it's simply this object was set in motion. So I'm seeing this piece of metal move. It means that this magnet applied a certain force on this piece of metal, but yet they are not in contact. There is a distance between them. There's a gap. There's some space. This is what we call forces acting from a distance. Forces that exist between 2 bodies without being in contact. So we're going to get to know all about these forces. So we are starting off with the contact forces. We are in this lecture, we're going to talk about three contact forces. So let us start with the first one. It is called tension force, T. So what do you mean by tension force? Its symbol is T with an arrow above it, which means that it can be represented by a vector. So what do you mean by tension force? A tension force is the force that is exerted by a spring, a string, a thread, a rope, a chain, all that. What do you mean by that? Let me give you an example. Okay, we know necklaces, right? So let's say this is a necklace. Okay, so a necklace, it consists of a chain, right? Or maybe we call it a thread, you can call it whatever. So it's a chain, and we have a certain, like a jewelry piece at the bottom, which we call pendant, okay, or a piece of jewelry. Now the thing is, I want to ask, okay, so if the chain didn't exist, so if there is no chain, what will happen to the piece of jewelry, or what will happen to the pendant? It will fall down to the ground, right? Nothing is preventing its motion. It will simply just fall down to the ground. Try holding a piece of jewelry and letting go of that piece. It will fall to the ground. But when we put it in a chain, okay, or in a thread, or in a string, then it won't fall anymore. Something is preventing its motion. Something is preventing it from falling. So something is applying a force on it. This is the ta-da-ta-da, it is the tension force. So the tension force, the chain, is applying a tension force on this piece of jewelry, and it is preventing it from falling. So this is the tension force. Let us take the first case. In the case of a tension force, we're talking about two cases today, okay? Which are the string case that we are interested in, and the spring case, which is very important as well. So these are the two cases that we're going to be discussing today. So the first case, the string case, we can see that we have, this is like a ceiling, and this is a string, and there is an object hanging, um, just from a string, and this is another wall. This is a wall and another object that is attached to this string, okay? So I know that if the string didn't exist in both cases, then both objects will fall to the ground. But something is preventing their motion, and it is the force that is exerted by the string on them, which is the tension force. So first of all, we said it's a contact force. So the point of application of the contact force is the point of contact. So what is the point of contact between the string and the object? It is right here. This is where they meet. This is the point of contact. In both cases, it is the point where they actually touch. Great. Now, what do you think is the line of action? The line of action of a tension force is always along the string. So it's somewhere along the string, okay? So it is like that. In this case, it is vertical. In this case, it is like oblique. How about the direction? Let me ask you something. We said that this string is preventing the object from falling. So the object is supposed to fall down, but the string is pushing it upwards. Okay, so it means that the direction is, how is it? It is towards the inside of the string. Okay, so it's always pushing towards the inside of the string, just like that. So if I want to represent them, they will look like that. So let's talk about the characteristics, which we already said. The point of application is the point of attachment or the point of contact between the string and the object. Line of action, it is along the string, and the direction, it is towards the inside of the string. Okay, it's always towards the inside of the string. Okay, so the case of a spring is Mm, like a bit similar to the case of a string, okay? But the thing is, with a spring, we have two cases, the case of a compressed spring and the case of an elongated spring, okay? Now, let me just stop this. Okay, now you see this blue arrow. Okay, so this blue arrow represents the tension force. Now I know it's not drawn here at the point of application, so this is not the actual representation of a tension force, but it's more clear to see it that way. Okay, just here. So let's see the case of the elongated springs. Now what do you see? I see that the tension force is along the spring. Okay, you can see that it is along the spring. Its point of application, of course, it will be the point of contact, this point between the spring and the object. And yeah, so its direction is towards the inside of the spring. See, it's going towards. Let's stop it. So it's going like this, so towards the inside of the spring. So this is exactly the same as the case of the string. It's exactly the same. So in case of an elongated spring, it is the same exact case as the string. Now, in case of a compressed spring, what is happening? You can see that the tension force is switching directions, right? So now it is along the spring, its line of action is along the spring, but now its direction is what? It's toward the outside of the spring. Okay, so it's going outside. You can try it at home if you have a spring. When you actually compress it, you feel that there is a force pushing your hand out. There is a force pushing, towards the outside. So this is the tension force that we're talking about. Okay, so yeah. This is the tension force. We have two cases in case of a spring. This is the case of an elongated spring, and this is the case of a compressed spring. Okay. So as we saw in the simulation, by the way, guys, you can try it out. You can simply click on that using the PowerPoint PDF that I sent. Okay. And yeah, so as we saw, we have two cases in the case of a spring. We have the case of an elongated spring, which is the same case as a string, right? It acts the same way. So when I have an object that is hanging from a spring, just like that, it means that it is kind of pushing down, but the spring is pushing upwards. It is preventing this object from falling. And yeah, so it is pushing upwards. In this case, it is pushing upwards because the spring is elongated. So we say that the point of application is the point of attachment. The line of action is along the spring, and the direction is towards the inside of the spring. So it is the same case as the string. Okay, it's always like that. Even if I have, let's say, I'm going to give another example here. Let's say I have this is a spring that is elongated, okay, and I have an object right here. It means that this is the point of application, and the line of action is along the spring, and it is towards the inside of the spring. See how? So, it's these things like don't change, okay? Case 2 is the case of a compressed spring. So let's take this example. We can see that this hand is pushing the object upwards. So the spring in this case, it is not elongated. It is now compressed. And in the case of a compressed string, first of all, the point of application will be the same. It is the point of attachment, the point of contact. This is where the force, tension force is applied. The line of action, it is still the same. It is along the spring, right? Line of action, in this case, it is vertical. The direction is what changes, only the direction. So in this case, when you actually try to push the box upwards, you will feel that there is something pushing your hand downwards. Something wants to like get out or something. So this force that you feel is the tension force, because in this case, the tension force will be pushing outwards. Okay, so it will have a direction towards the outside of the spring. Its point of attachment, it is the point of application, and line of action will be along the spring, but the direction is what changes. This is very important, okay, because it becomes towards the outside of the spring, just like that. The second contact force that we're going to talk about is the normal reaction N. So have you ever thought like why your book, let's say your book is resting on a table, like why your book is not falling down? Because the table is preventing it from falling. So the table is kind of exerting a force on it, and this force we call it a normal reaction, okay? We are preventing a certain motion. So normal reaction is the force exerted by a support on a body resting on it. So any support where a body is resting on the support, sitting on the support, okay, it means that the support is exerting a force on this body. The support could be a table, floor, wall, inclined plane, anything. Okay, so it's a contact force. We know that. It means that there is a contact between the body and the support, of course. Now, this point of contact between the body and the support is the point of application. Now, the normal reaction is perpendicular to the support. It's always perpendicular to the support and directed from the support towards the body. It's like pushing the body upwards or sideways or whatever, okay, the direction is, but the point is it's always perpendicular. How about this case? The second one, same. So the normal reaction is always perpendicular to the support. As you can see, it's directed from the support towards the body. And the third case, you have a cup of, let's say, tea or coffee, okay, and it's sitting there on a table. There is a normal reaction exerted by the table on this cup, and it is perpendicular to the support and directed from the table towards the cup. So if you want to write the characteristics of normal reaction, it would be that the point of application, it's the point of contact, but sometimes the point, there is no point of contact. Sometimes there is like a surface of contact. See, in this case, we have a surface. We have like, this is the contact surface. It's like a square. Okay, so the point of application, it should be like the center of this surface. So it is the center of the contact area between the support and the body. Line of action is perpendicular to the support. It's always perpendicular to the support. Okay, and the direction is from the support to the body. And the third contact force is the muscular force, F. From the name of it, it is the force that results due to the action of muscles. So actually, the action of muscles is exerting that force, okay? Let's look at the cases. Here we have, this is a spring balance, okay? And I'm kind of pushing it like this horizontally. The point of contact, the point of application is the point of contact. It is this point, and I'm pushing it outwards like this. So it depends. Each case is different here, okay? There is no just one known case, not like the normal reaction or the tension where I know how to draw it in each case. Here it is different. It depends how am I pushing, where am I pushing, in what direction, okay? So this is the first one. You can see here, this boy is pushing like this towards the left, okay? This case also, and here he's kicking a ball, so he's doing some muscular force on the ball, okay? And yeah, so each case is different. Now in this in the exercises, we're not gonna use this type of contact forces, okay? But it's good that we know it. So that is it. We're done with this week's lecture. I hope you guys find this interesting because it really is. And yeah, I hope you understood it. I'll see you guys in the Zoom live. Try to solve the worksheet. And yeah, so I'll see you later. Bye-bye.